Hello, this is exercise 3 from this week. Exercise 3. And in this exercise, we are given a curve, K, defined as a set of points where x squared plus y squared is equal to 1 and z is equal to 1. You see, x1 plus y1 squared is equal to 1 is the unit circle, but it is elevated to the plane z equal to 1. Let's try to draw this. We have here the x, y, z coordinate system. And then if we take 1 along the axis, then this circle will be with these diameters in the z equal to 1 plane. So it will look something like that in this perspective here. It will be an ellipse. So this is K. And we want to calculate the circulation of a particular vector field. And this is a nasty piece. Let me show you this. X, comma, y, comma, z. And this is y, and then the exponential function of x times y plus z squared. And then it's x and then plus z squared plus x as the second coordinate, and finally 2x squared plus 2y squared. And we want to calculate the circulation along K, and we can do that, and we want to do it with applying Stokes. And what we want to do is that we want to show that this is independent of the actual surface that has K as the boundary. And so we intend to use two surfaces. The one surface is simply the unit disk in this z equal to 1 plane. And it has, I call this surface F1, and it has the parametric representation of U, V. You see, you have the normal unit disk in the XY plane. And then the third coordinate is 1. And U belongs to the interval from 0 to pi half, and V belongs to the interval from minus pi to pi. So this is the one, and what we choose here to try as the second one is the semi or hemisphere above of unit radius, but above K. Let me try to, I can perhaps draw this in blue. Let's see how that looks. So it will look something like this. So it will be, and this is F2, and this one here is F1. But here we just take cosine U, sine B, sine U, cosine. Let me sine V, and then finally cosine V. This is the normal, say, unit sphere, but it's displaced by 1 in the z direction. And you have U, this belongs to the interval from 0 to pi half, and V belongs to the interval from minus pi to pi. So these are the two parametric representations for the two surfaces that will, so to speak, span or is spanned by K. And let's see how that looks. In order to use Stokes' theorem in order to calculate the circulation along K, we need the curl of V. So you have the V vector field. See, this is the Nabla operator times the V. Let me take this away. And so this will be Ex, Ey, Ez cross our V vector. I have the V vector here. I write it again. Y e to xy plus z squared, and then x to, and then e to xy plus z squared plus x, and then finally 2x squared plus 2y squared. And if you compute this, you get 4y minus 2z, 2z minus 4x, and the third coordinate becomes 1. So, and you can see that the curl of V is much simpler than the vector field itself. And this is one of the reasons why it is good to apply Stokes' theorem in this case. Now, in order to use Stokes' theorem, we need to have the normal vector to your surface. And let's compute this for the first of the two surfaces. You have that this is R prime U cross R prime V. And for the first, you get, when you differentiate with respect to U, you get cosine V, sine V, and then you get 0. And then when you differentiate it with respect to V, you get minus U sine V, and then you get U cosine V and 0. And you see, because of this, of the third coordinate being 0, there will be zeros in the first two places, and the final one, you will have the determinant of the other two coordinates And so this will be u times cosine squared plus u times sine squared. So this will be u when you calculate this. You can see u is positive. So the normal vector is pointing, say, if I draw this by red in the figure, this normal vector, then this will be pointing in that direction, and this means that the orientation of k for the circulation, when you use Stokes, will be in the positive, the counterclockwise direction. So this is okay, but you should remember that when you calculate using the other surface in order for the comparison to work. So let's try to calculate this circulation. And this will be the flux or the curl flux along the surface F1. And let me show you this, because we have the integral from minus pi to pi, and then I have the integral from 0 to from 0 to 1, and this will be the curl of my vector field, target the dot product with the normal vector, and then you should integrate with respect to u and v with these respective intervals. But when you look at it, here you have the curl, and here you have the normal vector. When you take the dot product, you simply get, because you have the two zeros in normal vector, you get u as the integrand. So this integral here is the integral from minus pi to pi and from 0 to 1 of u times du dv. And this will be minus pi to pi of 1/2 u squared between 0 and 1. And this is simply, there's nothing from the lower limit. So it will be 1/2, and then the integration of, so it'll be 1/2, and then the integration along b will be 2 pi. So this will be pi. So this is the circulation. Now let's see if we get the same circulation if we use the other surface. And I have calculated the normal vector for the other surface. And this is simply minus cosine u sine squared of v, and then minus sine of u sine squared of v, and then minus cosine v sine v. So if you look at this, and normally you would have Maple computing this, and then you can illustrate and so forth. But when you look at it, the first and second coordinate, since sine squared is positive, is pointing, you see in the xy plane, it's pointing towards the origin. And the third coordinate is pointing in the negative direction. So it is the inward pointing normal. And this will correspond to a negative orientation of the curve K. And if you want to compare it to the other calculation, then we need to use the outward pointing normal, which is then the negative of N2. So I write here due to the right hand rule, we need to use minus N2 in the integrand. And then the integrand becomes, it's n minus n2 of u comma v, dotted with the flux of v restricted to R2 of u. And when you compute this, you get 2 sine squared of v, and then you get sine of u minus cosine of u, and then finally plus cosine v sine v. And you see, the integral for v goes from 0 to pi half. And for u, it goes from minus pi to pi. And then I write here simply the integrand du dv. And you see, whenever you integrate sine, let me just take this, sine of u and cosine of u for a whole period, that is from minus pi to pi, you get 0. So the first term in this integrand doesn't contribute to the integral. So this is equal to the integral from 0 to pi half of, and then from minus pi to pi of cosine v times sine v du dv. Okay, and the integral from minus pi to pi half, the integrand doesn't depend on u, is simply 2 pi. And then you get the integral from 0 to pi half, cosine v sine v dv. And then if you use substitution, for instance, you get 2 pi and then 1/2 sine squared of b. Try to differentiate 1/2 sine squared of b, then you get 2 times 1/2, that is 1, you get sine of v, and then times cosine of v. So this is an antiderivative of cosine v, sine v, and you take it between these limits. So this is again equal to pi. So in this example, we have seen that using Stokes' theorem, you get the same curl flux independent of the spanning surface that you're using for your curve K, and this will give you the circulation. Okay,